Lesson 3.2 Hugging Face Datasets Overview. The dance behind it is fascinating. Through careful analysis and practice, you'll master these techniques quickly. The Datasets library from Hugging Face is the industry standard for working with training data. It makes loading, processing, and saving datasets remarkably straightforward, and it's engineered specifically for large datasets that would never fit in RAM. This lesson runs about 30 minutes and is aimed squarely at beginners, so we'll build everything from first principles, learning objectives. By the end of this lesson, you'll be able to load datasets directly from the Hugging Face hub, load local files in JSON, JSON-L, CSV, and Parquet formats, explore and inspect dataset structure, filter and sample records, create proper train and validation splits, save processed datasets for training, and use streaming to handle files that are larger than your available RAM. Why use Hugging Face datasets? There are 6 reasons this library has become the default choice for fine-tuning work. It's memory efficient. Data is loaded on demand rather than all at once. It's fast thanks to optimized caching and parallel processing. It's flexible, supporting virtually any file format you'll encounter. It supports streaming, so you can work with datasets larger than your RAM. It ships with built-in tools for filtering, mapping, and splitting. And it integrates seamlessly with Unsloth and the broader Hugging Face ecosystem. Here's the core problem this library solves. The traditional approach, reading a JSON lines file line by line into a Python list, loads everything into RAM simultaneously. With a 10 GB dataset, that means 10 GB of RAM consumed before you've done a single thing with the data. Systems slow down, processes crash, and you've wasted minutes just getting to square one. The Hugging Face approach uses memory mapping and lazy loading. When you call load_dataset, it doesn't pull the entire file into memory. Instead, it maps the file on disk and only reads the specific rows you actually request. A 10 GB file might consume as little as 100 MB of RAM. That's not a minor optimization. It's the difference between a workflow that runs and one that doesn't. Installation. Elaine says this cell installs the Hugging Face datasets library using pip with the quiet flag to suppress installation noise, then imports it and prints the version. The version print is the important part. You want to confirm you're on 17.0 or newer. If the number is lower, the installation in module the second of may not have completed correctly, and you should rerun the install before continuing. Loading datasets from Hugging Face Hub before writing a single line of code, it's worth knowing what's available to you. Head to huggingface.co/datasets and use the search bar. The terms instruction and chat surface conversational and instruction following datasets, exactly the shape of data most fine-tuning projects need. Search code for programming datasets or use domain terms like medical or legal to find specialized corpora. There are over 100,000 public datasets waiting there. This cell loads the Llama/Alpaca clean dataset, one of the most widely used instruction following datasets in the fine-tuning community. The load_dataset call handles everything: downloading, caching. The print statement at the end is your first sanity check. You should see a dataset dict containing a train split with features named instruction, input, output, and text, and a row count of 51,760. If you see that structure, the data is ready to work with. What you're seeing in the output is the dataset dict structure. Notice the 4 feature columns: instruction, input, output, and text. Each one is a value of type string. The instruction field tells the model what task to perform. The input field provides optional context. The output is the target response the model should learn to generate. The num_rows value of 51,760 confirms this is a substantial dataset, more than enough for meaningful fine-tuning. This cell does two things. First, it pulls the very first example from the training split and prints it. This reveals the exact key names and data format which you'll need to reference correctly in every downstream operation. Second, the loop prints the first three examples with output truncated to 100 characters. The truncation keeps the display readable while still giving you a representative sample of what the model will be learning from. Spend a moment actually reading these examples. They tell you more about data quality than any statistic. Many datasets on the hub ship with multiple splits, train, validation, test, and some have multiple configurations entirely. By passing splits train explicitly, you're being precise about which subset you want rather than accepting whatever the default happens to be. The OAST1 dataset and the Alpaca cleaned dataset both follow this pattern. After running this cell, you'll have two independent dataset objects ready for processing. Loading local datasets. While these ASH, the load_dataset function handles local files just as gracefully as remote ones. For a single JSON lines file, pass the format string and the fail name. For a dataset split across multiple files, common when datasets are large or distributed, pass a list of fail lines and they're concatenated automatically. When you have separate files for training and validation already, pass a dictionary mapping split names to file paths. Running the print statement after loading a dict-style dataset will show you a dataset dict with named splits, confirming everything is wired up correctly. Standard JSON files sometimes wrap the array of records inside a top-level key, something like data rather than a bare array. The field parameter handles exactly this case. By passing field data, you're telling the library to descend into that key and treat its contents as the actual records. Without this parameter, the loader would try to interpret the entire JSON object as a single example and fail. Check your JSON structure first, then set field accordingly. Loading a CSV file follows the same pattern. Specify CSV as the format and point to your file. The additional options shown here handle two edge cases. The delimiter parameter is technically redundant for standard CSVs since comma is the default, but making it explicit removes any ambiguity. The quoting option set to 1 corresponds to csv.co_ALA, which tells the parser that every field is wrapped in quotes, important if your text fields contain commas themselves. The output will confirm how many rows were loaded and what columns were detected. Parquet is the format you'll want for large production datasets. It's columnar, compressed, and dramatically faster to read than JSON or CSV for analytical workloads. Loading it is identical to any other format. Specify Parquet and point to the file. If you're working with datasets in the hundreds of megabytes or larger, consider converting to Parquet once and benefiting from the faster load times on every subsequent run. Windows paths are a common source of frustration here. The / character is an escape sequence in Python strings, so C uses name dt at a JSON-al is not what Python thinks it is. 3 clean solutions. Use forward slashes, which Windows accepts perfectly well. Prefix the string with R to make it a row string where backslashes are literal, or use pathlib's path class and convert to string. All 3 approaches work identically. Pick one and be consistent throughout your project. Exploring dataset structure. Once a dataset is loaded, the first thing to do is understand its shape. Checking dataset.keys.aca tells you which splits exist. Accessing the train split and calling len gives you the total row count, in this case 500 examples. The features attribute describes the schema, column names, and their data types. The column_names property gives you a plain list of those names, which is what you'll reference when filtering or accessing specific fields. These 4 checks take 10 seconds and save you from confusing key errors later. Accessing individual examples works like indexing into a dictionary of lists. Dataset train returns the first row as a Python dict. Dataset train returns a batch, but notice the structure flips. Instead of a list of dicts, you get a dict of lists where each key maps to a list of 5 values. That's the arrow-backed columnar format surfacing. The loop at the end iterates row by row and breaks early when it encounters an instruction longer than 100 characters. A quick way to scan for outliers in your data without printing thousands of lines. 3 quick quality checks worth running on any new dataset. First, len on the training split gives you total example count, the baseline number you'll reference throughout. Second, counting missing values in a column like input tells you how many examples lack that field, which matters if your training template assumes it's always present. Third, pulling unique values from a category column, if one exists, shows you the distribution of classes. An imbalanced category distribution can quietly bias your model, and catching it here costs nothing. Filtering and sampling. 2 ways to take a subset. The select method takes a list of integer indices and returns exactly those rows. Dataset train select train, the select train, 100 examples with for a random subset. Generate random indices with random.sample, then pass them to select. The key detail: random.sample without replacement guarantees no duplicate rows in your sample, which matters when you're building evaluation sets. Both operations return a new dataset object. The original is never modified. The filter method takes a function that returns true or false for each row and keeps only the rows where the function returns true. Filtering for instructions shorter than 50 characters isolates concise, direct prompts. Filtering for the word medical in either the instruction or output carves out a domain-specific subset without touching the original data. Filtering for outputs longer than 200 characters selects detailed, substantive responses, often higher quality for training. Each filter call returns a new dataset object, so you can chain them or apply them independently. For large datasets, filtering can be slow because it defaults to a single process. The num_proc parameter enables parallel processing across multiple CPU cores. On Windows, set this to 4. Matching or slightly below your physical core count is the right target. You'll see the progress bar split across multiple workers and the total time drops proportionally. The output after filtering confirms exactly how many rows pass the condition, so you know immediately whether your filter logic is doing what you intended. Reproducible sampling requires 2 steps: shuffle first, then select. Passing a fixed seed to shuffle ensures that every time you run this cell, the rows appear in the same randomized order, critical for comparing experiments. Selecting the first 100 rows from a shuffle dataset is equivalent to a random sample but deterministic. The alternative shown here, using train_test_split with a test_size fraction, handles the math for you when you want a percentage rather than a fixed count. The print confirms how many examples ended up in your sample. Shuffling. 2 shuffle patterns worth knowing. Passing seed =42 produces a deterministic shuffle. Run it 10 times, get the same order every time. This is what you want for reproducible experiments and published results. Calling shuffle without a seed produces a different order on every run, which can be useful for data augmentation or when you deliberately want variance between training runs. The crucial implementation detail: shuffle does not copy the dataset. It creates a new index mapping over the existing data, so memory usage barely changes even on a 10 GB dataset. Shuffling matters because real-world datasets are almost never randomly ordered. Instruction datasets are often grouped by topic, CSV exports are sorted by date, scrape data clusters by source. A model trained on ordered data learns the ordering pattern rather than the content. Shuffling before training is standard practice, not optional hygiene. Train validation splits. The train_test_split method on a dataset object works analogously to scikit-learn's version. Passing test_size equals sign 0, 2 allocates 20% of rows to the test key and 80% to the train key. The seed parameter locks the split so it's reproducible. After the split, printing the lengths of both subsets is the essential verification step. Confirm that the numbers add up to your original total and that the ratio looks right before saving anything. A silent off by 1 or an incorrect seed can corrupt your entire training run downstream. When you already have separate files for training and validation, a common situation when datasets are distributed this way, pass a dictionary to the data_files parameter with the keys train and validation pointing to their respective file paths. The resulting dataset dict will have those exact split names, and you can extract them with dataset train and dataset validation. No splitting math required and no risk of data leaking between splits. For a three-way split, train, validation, and test, the cleanest approach is 2 sequential calls to train_test_split. The first call divides the full dataset 70/30. The second call divides the 30% remainder evenly, producing 15% validation and 15% test. Using the same seed for both calls is important. It ensures the splits are reproducible as a unit. The final print confirms all 3 sizes. Add them up mentally. They should equal your original row count exactly. Saving datasets. Saving to JSON lines is the most common choice for fine-tuning workflows because the format is human-readable and universally supported. The basic to _JSON call writes the file, but the options shown here matter. Setting force_ASCII false preserves Unicode characters. Without this, any non-ASCII text gets escaped into unreadable sequences. The orient records and lines =true combination produces one JSON object per line, which is the JSON-L format that Unsloth and most training pipelines. The output file will appear in your working directory immediately after the cell completes. Saving to Parquet is a single method call to _Parquet with a fail main. The resulting file will be significantly smaller than an equivalent JSON-L file due to columnar compression, and it will reload dramatically faster on subsequent runs. If your dataset will be processed multiple times, which is typical during iterative fine-tuning experiments, saving once as Parquet and reloading from it each time is a meaningful time investment. Saving to CSV uses to _CSV with index =false. The index =false argument is important. Without it, the row numbers from the dataset's internal index get written as an extra column in your CSV, which then shows up as a spurious feature when you reload the file. Always pass index =false unless you have a specific reason to preserve the index. The save _to_disk and load _from_disk pair is the most efficient option when you're saving a full dataset dict, all splits together, and plan to reload it in Python. The format is arrow-backed and preserves the exact dataset structure, including all metadata. Reloading with load _from_disk is faster than any of the text-based formats. The trade-off is portability. The save directory is not human-readable and is intended for Python consumption only. For sharing with others or long-term archiving, JSON-L or Parquet is the better choice. Dataset streaming. For large datasets, streaming is the right tool in 3 situations. The dataset is larger than your available RAM. You want to start iterating over examples before the full download completes, or you're exploring a massive public dataset and only need a small sample. In all 3 cases, Streaming lets you work with data that would otherwise be inaccessible on your hardware. Adding streaming equals sign true to a load underscore dataset call changes the return type from a dataset to an iRable dataset. The data is never fully downloaded or loaded into memory. Rows are fetched and decoded one at a time as you iterate. The for loop here prints the instruction field from each streamed example and breaks after 10 iterations, giving you a quick preview of the data without triggering a full download. Notice there's no len call and no index access. Those operations don't exist on streaming datasets, which is the main constraint to be aware of. For local large files, streaming works identically. Pass the file path, set streaming equals sign true, and you get an iRable dataset backed by your local file rather than a remote server. The iSlice call from ititools is the idiomatic way to take a fixed number of examples from a stream. Here, the first 1000 rows are materialized into a list. This is the pattern for converting a stream into a concrete in-memory subset. Stream the full file, slice what you need, work with the slice normally. 3 important limitations of streaming datasets. Random access by index dataset does not work, you can only iterate forward. Shuffling is limited to a buffer-based approximation rather than a true global shuffle. And len returns nothing because the total size may not be known until the stream is exhausted. The practical workflow: use streaming to explore and sample from large datasets, then download and process normally once you know exactly what subset you need for training. Practical examples. This example walks through a complete local dataset workflow. After loading from a JSON-L file, the code prints the split names, feature list, and total row count, your 3-point confirmation that the load succeeded. It then previews the first 3 examples to verify the instruction, input and output fields look correct. The conditional split logic checks whether the dataset is large enough to justify a validation set before attempting the split, a sensible guard that prevents errors on small test datasets. Both splits are saved as JSON-L files, and a confirmation message marks the end of the pipeline. This example demonstrates targeted domain filtering on a public dataset. Starting with the full 51760 example alpaca cleaned dataset, the filter function checks each row for programming related keywords, program, code, Python, function, algorithm in either the instruction or output field. The output tells you exactly how many examples matched. From that filtered subset, 500 examples are selected randomly via shuffle and select, then saved to a JSON-L file. This is the full pipeline for carving out a domain-specific training set from a general-purpose dataset. Combining datasets from different sources is a common requirement when no single dataset covers your use case. This example loads 2 separate JSON files, one for customer service, one for technical support, and prints the size of each to confirm they loaded correctly. The concatenate underscore datasets function merges them into a single dataset. After concatenation, shuffle with a fixed seed randomizes the combined data so examples from the 2 sources are interleaved, then train underscore test underscore split creates an 80/20th split. The final print confirms the sizes of both resulting splits. Format conversion is frequently necessary when your source data doesn't match the instruction input-output structure that fine-tuning templates expect. This example loads a question-answer dataset, then defines a convert underscore format function that maps each example from a question/answer structure to the instruction/output input structure. The map call applies this function. The input field is set to an empty string rather than omitted entirely. Many training templates expect the key to exist even when there is no value. The converted dataset is saved to a new JSON-L file ready for training. Hands-on exercise. This exercise loads the Tatsu Lab /Alpaca dataset and walks through 5 inspection tasks. Print the total number of examples to understand the dataset scale. Print the column names to confirm the schema. Display the first 5 instructions to assess content quality. Filter for examples where the input field is empty. This tells you how many examples are instruction only with no additional context. Then count the complement, examples with non-empty inputs. That ratio tells you how the dataset is structured and informs how you should design your prompt template. The solution loads llama/alpaca cleaned, targeting the train split, then works through each task in sequence. The total count of 51,760 confirms the dataset loaded in full. Printing column underscore names reveals the 4 fields. The slice dataset 5 instruction retrieves the first 5 instructions as a list in a single operation. The filter for empty inputs uses a lambda that checks whether the input field is an empty string. The count of non-empty inputs is the complement. Subtract from total to get the empty count, or filter separately and compare. Both numbers together characterize the dataset structure completely. The second exercise uses your recipe dataset from lesson 3.1. The goal is to run a complete data pipeline: load, filter, shuffle, split, and save. The pipeline has 5 steps. Load recipe underscore assistant underscore dataset.jsonl from your working directory. Filter to keep only examples where the output field exceeds 50 characters. This removes thin, low quality responses. Shuffle with split 80/20s into training and validation sets. Save both splits as JSONL files. Each step builds directly on the previous one, and the result is a clean split dataset ready for the training lessons ahead. The solution implements each pipeline step explicitly. After loading, the initial example count is printed as a baseline. The filter lambda checks output lengths against 50 characters, and the post filter count shows you exactly how many examples survived, giving you a concrete sense of your data quality. The shuffle with seed =42 is applied before the split, which is the correct order: shuffle first, then divide, so both splits contain a representative mix. The 0.2 test underscore size produces an 80/20. Both resulting datasets are saved with descriptive fail mines, and the completion message confirms the pipeline finished without errors. Common issues and solutions. Here's a mistake that catches nearly everyone the first time. Loading a JSONL file without specifying a split returns a dataset dict, not a dataset. Trying to index into a dataset dict with dataset var raises a kick here because the valid keys are split names like train, not integers. The error message will mention that the key 0 doesn't exist and will list the actual keys. That's your signal that you need to go one level deeper. 2 clean fixes. Either access the split explicitly, dataset train 0, or add split train to the original load underscore dataset call, which returns a dataset directly rather than a dataset dict. The second approach is cleaner when you know you only need one split. Either way, the print statement should now output the first row as a Python dictionary without any errors. Windows file paths with backslashes cause a subtle but consistent problem. The string cc users name.a.jsonl contains u, none, and dd, all valid Python escape sequences that get interpreted before the string ever reaches load underscore dataset. The result is a malformed path that the file system doesn't recognize, and you get a file font path even though the file clearly exists. This is one of those errors that looks mysterious until you understand escape sequences, and then it's obvious every time. 3 equivalent fixes, all correct. // c/usersname.jsonl work on Windows without any modification. A raw string prefix r/c/usersname.jsonl tells, and palef's path object handles the platform-specific separator internally. So path rcc users name / data.jsonl produces the right path regardless of OS. Pick whichever reads most natural. Attempting to load a 10 GB JSONL file with a standard load underscore dataset call will exhaust your system's RAM. With 48 GBs of RAM across your two P40s, you might get away with it, but you'd be consuming memory that your GPU training process needs. The safer approach is to never load large files this way in the first place. Use streaming to explore the data first. Determine what subset you actually need, then load only that subset. Two practical solutions for large files. The first uses streaming =true to iterate through the file without loading it into memory. You process examples one at a time and your RAM usage stays flat regardless of file size. The second uses pandas with navaras =10,000 to read only the first 10,000 rows into a data frame for inspection. Both approaches let you understand a large dataset structure and content without committing to a full load. Once you know what you need, you can load a targeted subset normally. A core on a field name usually means the column exists under a different name than you expected. Trying to access dataset trained response when the column is actually named output raises a core immediately. This is especially common when combining datasets from different sources, each with its own naming conventions. The diagnostic is straightforward. Print dataset train column names to see exactly what keys exist. Once you know the correct name, output in this case, access it directly. For defensive code that needs to handle inconsistent schemas, the dictionary get method with a fallback value is the right pattern. Example get response n/a returns n/a if the key doesn't exist rather than raising an exception. That's the difference between a pipeline that crashes on one bad row and one that handles it gracefully. Key takeaways. Tasansa fatir biljumenster, and practice you'll master these techniques quickly. 7 things to carry forward from this lesson. Use load underscore dataset for both local files and remote hub datasets. The interface is identical. JSONL is the most practical format for fine-tuning work. Always split into train and validation sets. 80-20 is the standard starting point. Shuffle before splitting to eliminate ordering bias. Use streaming for files that exceed your available RAM. Check column names before accessing data to avoid key errors. And on Windows, use // or raw strings in all file paths. Quick reference, key functions. Key functions. Here's the complete function inventory for this lesson. For loading, load underscore dataset handles local files and hub datasets with streaming =true for large files. For exploration, len features call for processing, filter for row selection, map for transformations, shuffle for randomization, for saving to _JSON to _parcours to _CSV and save to _disk. These are the 10 or so functions that cover the vast majority of dataset work you'll do throughout this course. Knowledge check. Before moving to the next lesson, confirm you can do each of these from memory. Load a local JSONL file into a dataset object. Access and print specific examples by index. Filter a dataset using a lambda condition. Create an 80-20 train and validation split. Save a processed dataset to disk. Use streaming to iterate over a large file. Handle Windows file paths without triggering escape sequence errors. If any of these feels shaky, the relevant section is worth a second pass. Assignment voice, went voice, voice. Build a complete data pipeline for your own project. Load your custom dataset from lesson 3.1, or create a new one. Print basic statistics, total examples and column names. Filter out any examples where the output is shorter than 20 characters. Shuffle the dataset. Split 80% for training and 20% for validation. Save both splits as JSON-L files. Then verify the save worked by reloading both files and printing their row counts. A starter template is provided below to get you oriented. The starter template handles the load and initial print, then marks the remaining steps with comments. Fill in each comment block with the appropriate function calls from this lesson. The structure is intentional. Each step builds on the previous output, so if something goes wrong, the print statements at each stage will tell you exactly where the pipeline broke down. The completion message at the end is your confirmation that all 5 steps executed without errors. What's next? You now know how to load, inspect, filter, split, and save datasets from both local files and the Hugging Face Hub. But all of those workflows assume the dataset already exists in the right format. What happens when you need to build your own training data from scratch? That's exactly what Lesson 3.3 covers, creating custom datasets tailored precisely to your use case. Additional resources. For deeper reading, the official Hugging Face datasets documentation covers every parameter and edge case in detail. The datasets GitHub repository is worth bookmarking for release notes and issue tracking. The Hub's dataset browser at huggingface.co/datasets lets you preview examples before writing a single line of code. The streaming guide and processing guide in the official docs are both worth reading once you've completed the assignment. They cover advanced patterns that will become relevant as your datasets grow. This diagram shows the Hugging Face ecosystem you'll be working within throughout this course. At the top sits the Hugging Face Hub, divided into 2 halves. The Dataset Hub with over 100,000 public datasets and the Model Hub with over 350,000 models. Below that are the core Python libraries, Datasets, Transformers, PEFT, and Accelerate, each handling a distinct layer of the fine-tuning stack. Onslaught wraps around all of them, simplifying the interface considerably. Understanding this layered structure matters because when something goes wrong, knowing which library owns which responsibility tells you exactly where to look. This diagram maps the complete dataset loading flow from raw source to training-ready splits. It starts with a source choice, hub or local file, and flows through load_dataset into a series of transformation steps. Inspection first. Check features and shape before touching anything. Then map for preprocessing transformations, filter for removing bad rows, and apply _chat_template ANSI for tokenization. After those transformations, train_test_split ANSI. The final step is save _to_disk aka or push_to_hub. This sequence is not arbitrary. Each step depends on the previous one being correct, which is why the inspection step comes before any transformation. This chart shows a selection of popular open source fine-tuning datasets plotted by approximate example count. WizardLM, Oka, and UltraChat stand out at the higher end, larger datasets that tend to produce more robust instruction-following behavior. The color coding distinguishes dataset type: instruction following, chat, and reasoning. The type distinction matters for your use case. If you're building a conversational assistant, chat datasets are the right foundation. If you're fine-tuning for complex multi-step tasks, reasoning datasets like Oka are worth investigating. Knowing what's available before you commit to a dataset saves significant time. This diagram illustrates the standard dataset splitting strategy for fine-tuning. The training set takes 80% of your data. This is what the model actually learns from. The remaining 20% is divided evenly. 10% for validation, used to monitor performance during training and tune hyperparameters, and 10% for the test set, held out completely until final evaluation. The critical rule: The test set must never be seen during training or hyperparameter tuning. Any contamination between splits produces optimistic metrics that don't reflect real-world performance. Keep the splits separate from the moment you create them. This comparison makes the performance difference between full loading and streaming concrete. Full load, 48 GB of RAM, 120 seconds to first batch, 50 GB of disk space required. Streaming, 2 GB of RAM, 3 seconds to first batch, 0 additional disk space. The RAM difference alone is decisive for most workloads. Your P40s need that memory for model weights and activations during training, not for holding a static dataset. Streaming is not a workaround for unusual situations. For large datasets, it's the correct default approach. This table compares the 5 local dataset formats you'll encounter. JSON-L is medium speed, larger file size, but human readable, ideal for debugging and sharing. CSV is fast and familiar, best for tabular data. Parquet is very fast with compact storage, the right choice for large datasets and production workflows. Arrow format is the fastest for in-memory processing, which is what the datasets library uses internally. Plain text is variable in size and suited for raw pre-training corpora. For fine-tuning specifically, JSON-L for development and Parquet for production is a sensible default strategy. This diagram maps the filtering and sampling functions onto the data flow. Starting from a raw dataset pulled from the hub, filter through extracts rows matching a condition. Select pulls rows by index range, giving you precise slices. Shuffle seed randomizes the order for unbiased training. Map applies a transformation function to every row. Format conversion, tokenization, field renaming, all of these operations feed into train_test_split, which produces the final training and validation. Each function returns a new dataset object, so you can chain them freely without modifying the original data. 2 splitting strategies, each suited to different situations. The standard October 10th 80 split, 80% training, 10% validation, 10% test, is appropriate when you have thousands of examples or more. The data scarce strategy shifts to May 5th 90, keeping 90% for training when examples are limited. The intuition, validation and test sets only need to be large enough to produce statistically meaningful metrics. A few hundred examples is often sufficient for that purpose, which means the rest can go toward training. Choose based on your total dataset size, not habit. This reference table summarizes the 5 save methods and when to use each. Save _ to disk is fastest for Hugging Face datasets and preserves all metadata. Use it when you reload in Python. _JSON produces human readable JSON-L. Use it for sharing and for training pipelines that expect text files. _CSV is the right choice for tabular data that needs to be opened in Excel or analyzed in Pandas. _Parquet gives the best compression for large datasets. Use it in production. Push_to_hub shares your dataset publicly on the Hugging Face hub. The reload method pairs with each save method. Load _from_disk for save _to disk and load _. This table is worth bookmarking. It maps the 6 most common dataset loading errors to their causes and fixes. Fall at water means the path is wrong. Use an absolute path and verify with os.listdr_temi. JSON decode error means at least one line in your JSON-L file is malformed. Use json.loads SNA in a loop to find the bad line. Value error with wrong column count means your CSV header doesn't match the data rows. Inspect the header and rename or drop columns. Keyquar on a field name means a column name mismatch. Use field_mapping or rename the column. CUDA OM Turing map means your batch size is too large. Add batched equals sign true with batch underscore size equals sign 32. Unicode decode error means non-UTF-8 characters in your file. Specify encoding equals sign UTF-8 neither or set errors replace.